Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. In this video, I'm taking a look at this two-part question on complex numbers. Part 1 says to factorise z to the 8 plus 1 into real quadratic factors. And then part 2 says show that cos of 4 theta equals 8 times cos squared theta minus cos squared pi on 8 times cos squared theta minus cos squared 3 pi on 8. Now, often with these kind of multi-part questions, the approach that you need for part 2, say, would require using what you worked out in part 1. And that may very well be the case for this question as well. But in terms of the approaches that I've taken, for part 1, I'll kind of work through and find what all these real quadratic factors are, but I won't actually rely on them to then get to this result in part 2. For part 2, I can actually show that this is true just using completely separate techniques. And whilst it probably would have been ideal to kind of link them up, I personally just can't find a way to kind of get to the result in part 2 using what we work out in part 1. So what I'll do is I'll tackle each of these parts in separate videos. I mean, part 1 is quite a lengthy question anyway, so these two parts probably needed their own video in any case. But because I'm not really going to link them up in terms of my approach, I think it makes sense to do them in 2 separate videos. Alright, so for part 1, we've been asked to factorise z to the 8 plus 1 into real quadratic factors, which essentially just means we want to have quadratics as the things that we're multiplying together, so things in a power of 2, and we want all the coefficients of, in this case, z to be real. So we don't want any of the coefficients to have the imaginary number I in them. So, I mean, essentially what we're really trying to do is find the solutions of z to the 8 plus 1 equals 0, because once we have those solutions, we can then say z minus solution 1 times z minus solution 2, and so on. That is how you can factor this. And then presumably we'll have 8 of those. If we want to get quadratics, we're probably going to be multiplying some of them together to get into polynomials of order 2. And then the hope is that in doing that process, all the coefficients will be real. So somehow our imaginary numbers will kind of fall out. Now what we've got here, z to the 8 plus 1, it's very similar to what we're used to with roots of unity questions, which would be normally z to the n minus 1 equals 0. So we're going to use a similar approach to what we do with those roots of unity questions, just with a slight different tweak, because really what we're doing now is we're finding all the solutions of z to the 8 equals negative 1, where in our case we would let z equal the cis of theta, which is just shorthand for cos of theta plus I sine of theta. So if that's how we're going to define z, then we can say z to the 8 is equal to the cis of 8 theta, and that's using de Moivre's theorem, where you can bring the power into the argument. From there, we kind of basically just need to find our thetas, because we want z to the 8 equals negative 1, which means we want cis of 8 theta to be equal to negative 1. And we know that's going to happen when our 8 theta, our angle here, is equal to pi plus 2 pi times k, where k is an integer. Now that's slightly different to what we had with dealing with things like z to the 8 minus 1. Normally we'd just be setting our argument to just multiples of 2 pi. But here we need pi plus the multiples of 2 pi, and maybe it's worth just drawing a diagram of our cos and sine curves to really emphasize why that's the case. So just kind of draw enough so that we can see a few loops. So if I go pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, that's probably enough for enough loops. So I'll just call this x and y. I'll call this 1, 0, -1, and so we had pi, 2 pi, 3 pi, 4 pi, 5 pi, and 6 pi. I'll just maybe use some different colors. So let's draw the cos curve first. So we'd have the cos curve looking like this. And it's just periodic, so it loops around in the same pattern over and over. And it would keep going. So this is y is equal to cos of x. And maybe I'll draw the sine curve as well, maybe in red. So the sine curve follows the same pattern, it's just offset. And that's y is equal to sine of x. And the key is we're concerned with when our cis of 8 theta, or in other words our cos plus I sine is equal to -1. And you will see that that's going to happen at, in this case, pi, 3 pi, 5 pi, and so on. So this you could think of as pi plus 2 pi times 0. This is pi plus 2 pi times 1 to get 3 pi. And then pi plus 2 pi times 2 to get 5 pi altogether, and so on and so on. And notice that each time when the cos is at -1, the sine is at 0. So our cos plus I sine simplifies down to -1 at all points where the cos is -1 because the sine is 0. So hopefully that helps clarify why this is the format of our solution. All the values of 8 theta that would give the cos, or the cis of 8 theta of -1. So now if we just isolate theta, we can say what we want is theta being equal to pi plus 2 pi k on 8 for pi being, or for, yes, for, we want theta to be between -pi and pi inclusive. So that domain, that relates to the fact that we're looking at a full rotation around the axis in the Argand plane. So we're kind of going to get our going from 0 to pi, coming around anti-clockwise, and then from 0 to -pi, I guess you could call it, because these are all negative angles coming clockwise. So when you combine those two domains, you get your full rotation. So that's what we've got. We've got this theta in this domain. So if we just insert this value of theta into the domain, we'll be able to solve for the values of k that we care about. Once we get those values of k, we can then have our arguments. So we'll have -pi less than pi plus 2 pi k on 8 less than or equal to pi. I'll just bring the 8 up, so we'll get -8 pi less than pi plus 2 pi k less than or equal to 8 pi. -8 pi minus pi would be -9 pi less than 2 pi k less than or equal to 8 minus 1 is 7 pi. And then all of these pi's can cancel. And I can bring the 2 down and we'll get -9 on 2 less than k less than or equal to 7 on 2. And what that means is k will be equal to, k needs to be an integer. So -9 on 2 is -4.5. So the first integer above that is -4. Then -3, -2, -1, 0, 1, 2, 3. And that should be it. 1, 2, 3, 4, 5, 6, 7. That's 8 solutions. We know we have 8 solutions because we've got something to the power of 8. So that means our theta the thetas, the arguments will be, if I just get my calculator to make sure I get this right. So we're looking at pi plus 2 pi k on 8. So when k is negative 4, it would be, well, essentially 2 times negative 4 is negative 8 plus 1 is negative 7. So we'll have negative 7 pi on 8. Then we'd have 2 times negative 3 is 6, plus 1 is minus 5 pi on 8. Negative 4 plus 1, minus 3 pi on 8. And you see the pattern is we're just moving up in terms of 2 pi. So then we get negative pi on 8, pi on 8, 3 pi on 8, 5 pi on 8, 7 pi on 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's all our arguments of all of our solutions, our 8 solutions to this equation. So now what we can do is maybe I'll draw those up onto an Argand diagram because I think it's helpful to see really what we're dealing with here. So I'll just draw a small Argand diagram here. So we'll have our real and our imaginary. I'll just call this 1, 1, negative 1, negative 1. So I'll draw up my unit circle. And if I just get my calculator and work out the first angle that we're dealing with is, I'll start from these positive arguments so that we work around the Argand plane. So 180 divided by 8 is 22.5 degrees. So if that's 45, 22.5 should be about here. So I'll call that omega 1. If we look at 3 pi on 8, so 3 times 180 divided by 8, 67.5 should be about here. We'll call that omega 2 for the second solution. Now from here I can just kind of come across. That'll be omega 3. I can come across here. That'll be omega 4. Come down. Omega 5. Omega 6. Omega 7. And omega 8. So these are all the solutions to z to the 8 plus 1 equals 0. And I think the benefit of drawing them in this Argand plane is to really emphasize that essentially whilst we've got 8 solutions, we're really dealing with 4 pairs of complex conjugates. And I think it's focusing on these complex conjugate pairs that's going to allow us to eventually get to real quadratic factors because it's in letting those conjugates interact with each other that a lot of the imaginary numbers are going to disappear. And we'll see that play out as we start to work through this. So maybe what I'll do is I'll just note up a few of really what we're dealing with these solutions. So we've kind of got omega 1, omega 2, omega 3, and omega 4. I'll just focus on those for now. So remember our solutions are in the form cis theta or cos theta plus I sine theta. So omega 1 is cos pi on 8, cos pi on 8 plus I sine pi on 8. Then we've got cos 3 pi on 8 plus I sine 3 pi on 8. We've got cos 5 pi on 8 plus I sine 5 pi on 8. Then we've got cos 7 pi on 8 plus I sine 7 pi on 8. And that captures these 4. And then we could keep going with our negatives, but actually what I think is more helpful to note is simply that omega 8 is equal to the conjugate of omega 1. And omega 7 is the conjugate of omega 2. Omega 6 is the conjugate of omega 3. And omega 5 is the conjugate of omega 4. And we'll see why that's useful soon. But I think the next step, what we can do now, is we can say that our z to the 8 plus 1 can be written as z minus each of these solutions multiplied all together. So it'll be z minus omega 1, z minus omega 2, z minus omega 3, z minus omega 4. Now z minus omega 5, but omega 5 I'm just going to write as the conjugate of omega 4. And z minus omega 6 will be the conjugate of omega 3. Z minus omega 7 will be the conjugate of omega 2. And then z minus omega 8 is the conjugate of omega 1. And to really hone this in, I'm just going to write this out with each of our conjugates kind of being paired up. So we'll have z minus omega 1 times z minus the conjugate of omega 1 times z minus omega 2 times z minus the conjugate of omega 2 times z minus omega 3 times z minus the conjugate of omega 3. And finally, z minus omega 4 times z minus the conjugate of omega 4. And if we expand out each of these pairs, what we'll get is we'll get z squared, and we'll get minus omega 1 conjugate z minus omega z, which I can just write as minus omega 1 plus the conjugate of omega 1 times z. And then when we multiply them, the two negatives will become a positive, so we'll get plus omega 1 conjugate of omega 1. And that's going to follow the same pattern for all four of these pairs of factors. So we'll get z squared minus omega 2 plus conjugate of omega 2 z plus omega 2 conjugate of omega 2 times z squared minus omega 3 plus the conjugate of omega 3 z plus omega 3 conjugate of omega 3 times z squared minus omega 4 plus conjugate of omega 4 z plus omega 4 conjugate of omega 4. And so what's worth noticing now is that in each of our factors we've got quadratics, which is good because that's what we're after. We're after quadratic factors. Now we need to see are our coefficients all going to be real. So the coefficient of z squared in all of these factors is 1, so that's good, they're real. The coefficient of z, is this going to be real? And this constant over here, are they going to be real? If so, then we've got where we need to get to. And I might turn over because it's worth kind of going back to basics really. If we kind of think about our most basic definition of a complex number, z is equal to x plus iy. If that's the case, then our conjugate z bar would be x minus iy. And so if we wanted to take z plus z bar, that would become x plus iy plus x minus iy. So the imaginary parts cancel and we just get 2x. Or in other words, 2 times the real part of our complex number. So that's good. It means all of these instances where we're adding the complex number with its conjugate, they're all going to turn out to end up being real. Now if we look at z times z bar, that's going to be x plus iy times x minus iy, which will be x squared minus xyi plus xyi minus I squared y squared. These cancel, and we get x squared minus I squared, which is minus -1 or plus y squared. I'm going to write this as the square root of x squared plus y squared squared, so I haven't changed anything, but it helps us see that the square root of x squared plus y squared is the modulus of z. So that's going to be the modulus of z all squared. Now, now we can kind of put those results into our factors here. So what we can say is therefore z to the 8 plus 1 is equal to z squared minus 2 times the real part of omega 1. Now omega 1 we noted was cos pi on 8 plus I sine pi on 8, so the real part is this. So it's going to be 2 of that. So minus 2 times cos pi on 8 times z, and then finally we plus the modulus of omega 1. Now notice that all of our roots, they all lie on the unit circle, so all of them have a modulus of 1. So all of these are all just going to simply be the number 1. So that's a good sign because 1 is a real number. So here we've got a quadratic and all of the coefficients are real. So that's a good sign. And we're going to continue the pattern. So we'll get times z squared minus 2. In this case, the real part of omega 2 is cos 3 pi on 8. So cos 3 pi on 8 z plus 1, same modulus. Z squared minus 2 cos 5 pi on 8, z plus 1, and then finally z squared minus 2 cos 7 pi on 8, that's here, 7 pi on 8, z plus 1. So here we have our real quadratic factors. So we've got 4 factors here. They're all quadratics, which makes sense because we need 8 solutions, and 4 times 2 is 8. They all have real coefficients, so they're all real quadratic factors. Boom! So that's how you answer that question. I guess in the end, the key to it was just following our familiar process for roots of unity. Just tweaking it a little because now we're going after -1 instead of +1. But apart from that, you know, same kind of ideas, find all your solutions. It's often helpful to put them in the Argand plane around our unit circle. And really, the key to getting to all of the coefficients being real was really appreciating the fact that we have complex conjugate pairs, and noting these key results about how conjugates interact with each other and how the imaginary parts kind of fall away and you end up with everything being real. So hopefully that all made sense. If you found that explanation helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.